Our next talk is by Orna Grumberg. If you want to share your screen, we can make sure your slides are all working while I'm introducing you. So Orna is a professor in the CS department at the Technion. She is an ACM fellow and has been very influential in formal methods for many years now, and been on the steering committee of CAV and many other conferences and journals. Her textbook on model checking is a standard reference. And of course, she won the CAV award some years back for her extremely influential work on CGAR. Today, she's going to be talking to us about compositional model checking for multi-properties. We're very excited to learn more. Go ahead.
Hello, everyone. It's a pleasure to be here. I will talk about compositional model checking for multi-properties. This is a joint work with Ohad Holtzman and Sarai Schenwald, and Ohad also contributed the wonderful presentation that I have. So we all know that model checking is a procedure that obtains a description of a system and a property and result with a yes if the system satisfies the property, and with no otherwise, where hopefully in many cases it returns a counterexample. Trace properties like LTL, for instance, relate just to a specific trace. So for instance, they can express the fact that along a trace, two consecutive states satisfy P. On the other hand, they cannot express properties that relate different execution of the same program. So for instance, expressing that in every 2 runs of P, always at least one run can accept a request is inexpressible in LTL. For that, hyperproperties were suggested. They can relate different executions of the same program, and they can express, for instance, there is no leak, information leak from high variables to low variables. So we do not allow to have such a leak, and we can express it by saying that in every 2 executions that agree on the low action, the low variables are always equal. So now the model checking again receives a description of the system and the property, but now it's a hyperproperty, and return a yes or a no plus counterexample. And the traditional way to model check hyperproperties would be to have a composition of the model on itself as the number of quantification that appears in the LTL. And this is quite problematic because it makes the checked model very large and might make it the model checking infeasible. One way to avoid the state explosion problem is by abstraction. So the idea of abstraction is to take a model and to remove some of the unnecessary detail and to get some approximation. And there are 2 kinds of traditional approximation. The desired property of the abstraction is that if a property is hold of the abstraction, then we want it to hold also of the original model. And here we can see that we can either over-approximate the model by adding more behaviors that are not present in the original model, or we may produce an under-approximation of the original model where some of the execution of the model were removed. So the problem is that such abstraction will not work for hyperproperties in general. For instance, if we have a property where all quantifications are for all, then we could use an over-approximation because over-approximation just add more behaviors of the system, and if all behaviors of the over-approximation satisfy the property, then the original model also satisfies the property. Similarly, if all quantification are exist, then we may use an under-approximation because we have just removed some of the behaviors of the system. And if, in spite of removing several of the behaviors, we manage to prove the property, then it also holds on of the original program. The problem is what happens if the property is a combination of for all quantification and exist quantification. It is not clear how to have an approximation that will preserve this property, and we just don't know what to do. So in addition to this problem with abstraction, we have an additional problem with hyperproperties, and that is that it is limited in the way the type of properties that can be expressed naturally. So for instance, to say that two programs P and P prime are equivalent is not naturally expressed in hyperproperty. You could encode the behavior of P in a different way than the behaviors of P prime and then compare them, but it will not be a straightforward description of P is equivalent to P prime. Another property that was mentioned in the literature as a shorthand for hyperproperty is diversity, in which case we have a system with different low-level implementation, but they're all required to have the same high-level behavior. And this, again, is not naturally expressed by means of hyperproperty. So what we suggest in this work is to use multi-properties and multi-models. So multi-properties can refer to specific models in the system, and the system itself is explicitly described by a set of models. So it is not just one system, it is a set of systems that compose when composed just consist of the system, and the multi-properties can refer to such a system. So multi-properties will be interpreted over multi-models where there is a set of models, as I said, and the syntax of multi-LTL is just like hyper-LTL, except for each quantification, each quantifier has an index that says there exists a behavior belonging to the J's component that should satisfy the property, or for all behaviors belonging to a certain model, they should satisfy the property. Once we have multi-LTL, then we can express things like properties like liveness, kind of liveness for a communicating channel. Assuming that we have a server and a client, we can say every behavior of the client and for every behavior of the server, if we have a request from the client, then eventually this request is received by the client, by the server, meaning that requests are not lost via the channel. We can also naturally express program equivalence by saying that for every behavior of P, there is a behavior of P prime, so that if they agree on their inputs, then when they both ended, then they agree on the output. And in addition, for every behavior of P prime, there is a behavior of P that again agree on the input-output. So this is very natural. While in hyperproperties, you could do it by kind of encoding, adding more indexing. It will not be a straightforward hyperproperty description. What we found out, it's not very surprising, that multi-LTL model checking is reducible to hyper-LTL model checking and vice versa. So we didn't gain a new expressive power. And in addition, we did develop our own algorithm, which is directly applied to multi-LTL without the reduction, with the same complexity as hyper-LTL. And we have some benefit for this specific fragment that I will mention again and again, of for all star exist star, where we can extract also counterexamples for this property when it doesn't hold. However, the main benefit of multi-properties and multi-models is in the fact that the system itself consists of several models, and we can refer to each model separately. So we suggest a proof rule that applies abstraction, but also take advantage of the fact that we have several models and we refer to each model separately. So let's consider the following property just to get some intuition. It quantifies existentially over the first component. It has a universal quantification over the second component, and it says that globally, whenever we have a request from the first one, then eventually we will have a grant from the second. So assume that now we have, this is the first, the yellow is the first component and the blue is the second one, and we want to know whether the property holds, and assume that indeed we were successful to find a behavior, a yellow behavior, that with every blue behavior satisfy the property. So we are fine, we managed to prove the property. But now if we replace the blue model by an over-approximation, we add more behaviors, and now if we are still able to prove that for that there exists a yellow behavior that together with every blue behavior can satisfy the property, then we are fine, because we have here more blue behaviors than the original one, and if we manage to satisfy the property for each one of them, then we actually satisfy the property for the original behaviors. Similarly, we can reduce the first model. We can form an under-approximation by removing some of the yellow behaviors, and if with the under-approximation here we still manage to satisfy the property, then the original model also satisfies the property, because in the under-approximations, all the behaviors are real behaviors of the original model. We didn't add behaviors that were not in the original model. So what we suggest is to prove this kind of property with exist for the first one and for all for the second one by under-approximating the first one, over-approximating the second one, and if we are successful in proving it, the property for this under and over-approximation, then we can conclude that the property holds of the original model. Note that it might be the case that the same model is quantified several times, once with the exist and another time with the for all, and then we may apply different kind of abstraction to the same model. But it's very important that we handle each model separately. And when we compose the system, it's only we only compose abstractions, and we never compose the original models. Also, we should note, it might be confusing for someone that is not used to this notion, that even though we say that an over-approximation has more behaviors, the model itself is smaller in terms of state and transitions, but it has more behaviors. Consider of self-loop that can do everything, and then it represents many behaviors with very few states and transitions. So to just summarize what we said so far, once we have a model that is quantified with a for all, we apply an over-approximation. We write that the model satisfies another model when there is an inclusion in their behaviors, and when a model is quantified with their exist, then the abstraction is a subset of the behaviors of the model. So the proof rule, we have two proof rules. One is exactly what I described right now. We have, let's say, 3 components, and we want to know whether the property satisfies. Then assume that the property again is of the type of for all exist for all. Then we over-approximate the first one, we under-approximate the second one, and we over-approximate the third one. And if we manage to prove the property based on this abstraction, then we can conclude that the original model satisfied the property. We may want to refute the property, in which case what we are going to do is to consider the negation of the property. And if the property was for all exist for all, then the negation is there exist for all exist with the negation of the LTL part. And what we are going to do is to take an under approximation for the first one, an over for the second one, and an other for the third one. And in that case, if they satisfy not P, or actually does not satisfy P, then we can conclude that the original model does not satisfy P. So these are just the proof rules. I'll skip it. And now it is well known that when we use abstraction, it's a problem to come up immediately with a good abstraction which is strong enough. And what we need to do is to have a mechanism of counterexample guided abstraction refinement, or CIGAR, which allow us to start with some abstraction and then refine if necessary. So here is the framework. We start with a model and a property. We generate an initial abstraction and we apply model checking to it. If the model checking was not successful, then a counterexample is generated, and then we check whether it's spurious or not. If it's not spurious, then we have found a real counterexample and the model does not satisfy P. Otherwise, if the counterexample is spurious, then we want to eliminate it by refining the abstraction, and we come back to model checking. If the model checking finished successfully, then we know that the model satisfies P. So how do we apply every one of these parts in the context of multi-models? So the initial abstraction, for initial abstraction, we use a straightforward known type of abstraction. For over-approximation, we just have an existential abstraction. If there is a transition from a blue set to any blue state to a green state, then we have an abstract transition from the set of blue state to a set of green state. This will result in an over-approximating model. For the under-approximating, what we do, we have a transition from one abstract state to another if everyone in the first state has a transition to the second state. So this is for all exist a relationship between the states. Both of them are very straightforward to construct an over or an under approximation, and we use it. So we know how to generate an initial abstraction. We also know how to model check multi-properties. And now the question is what we do about counterexamples. So here we have two cases. If the property is universally quantified, then we may get a counterexample by just finding a tuple of words, one for each of the models that violate the checked property. Note that here as well, we have a compositional method because each of the counterexamples refer to one of the model. So this is again the advantage of having a compositional setting as we do for multi-model and multi-LTL. On the other hand, if the property consists of existential quantifier, then there is no better counterexample than the entire model, because in order to show that there does not exist a behavior that satisfies phi, then we have to show the whole model in order to prove that there is no such behavior. This is a well-known phenomenon. It already appeared in temporal logics like CTL or CTL star. Whenever we have an existential quantifier, then it's a problem to find a counterexample. So in general, we do not have a counterexample for multi-properties, but again, this nice special case of properties of for all star exists star, then we can extract a counterexample for all the existential part that appear first and to use it. So what we do here, if we have a property of the form for all star exist star, then we just extract a counterexample from the model checking. We note that this fragment is very useful for expressing many security properties. And we use a counterexample, in this case, coming from the model checking, W1 to WK. On the other hand, for general multi-properties, then what we do, we just extract counterexample heuristically, and the counterexamples coming from the symmetric behavior that tries to find a behavior of M1 that is not in M1 that is not in AI, or a behavior in AI that is not in MI. the symmetric difference, sorry. The advantage of this type of counterexamples is that they involve the model as well as the property. Here, the counterexamples are coming only from the model itself, but this is what we have at hand in this case. So as usual with the abstraction, we may get a spurious counterexample, and in this case we apply refinement, and this is again as usual if we have for instance a transition from S hat to Q hat, which shouldn't be there because not all the blue states have a transition to a green state, then we just split the abstract state and we remove the spurious counterexample. So this is not new, and I will not go over all the algorithm. We talked about most of it. The only interesting part is that we first apply model checking to the abstraction with P and return either a result or a counterexample for refinement. And in parallel, we could apply model checking for the dual abstraction with not P and return unsat if the model checking was successful, or a counterexample. So by that I finished the first part, which handles multi-models and multi-properties in the setting of infinite behaviors of reactive systems that are not necessarily terminating. But now we want to turn our attention to terminating programs where all behaviors are finite. And in this case, we will use automata, and we will use automata learning using L star in order to produce the over and under approximations required by the compositional proof rules. So the system itself is again a set of components, and each of the components is a non-deterministic finite automaton. And we take this set of non-deterministic finite automaton called multi-non-deterministic finite automaton, and we check whether a certain property holds. And the property is non-deterministic is described by a multi-non-deterministic hyperautomaton. So the model of non-deterministic hyperautomaton have been suggested previously by Borzou, that will give a talk in an hour or so, and by Sarai, which is our co-author. And we just extended it to multi-non-deterministic hyperautomaton, and the main difference will be this quantification. So the non-deterministic hyperautomaton is an automaton, but its input is not just one word, but a word, a sequence, a set of words, and we check them together. The automaton run on all the words together, and we have this quantification, and unlike hyper properties, here we have a name of the quantification for each of the quantification. We have the name of the model it refers to. So here we have a client and a server, and the client send request, and it is required that every request will eventually be followed by a grant from the server. So we see that as long as there is no request at all, then we stay in the accepting state. Once we have a request, but it comes together with a grant, then we still stay in the accepting state. If we have a request without a grant, then we are waiting for a grant, and once we see it, then we are going back to the accepting state. So for instance, if we are going to have two traces, one from the client and one from the server, then we see that on just on tau and tau, they stay in the first step, accepting step. Then seeing a request from the client, they move to the second one. We stay on the non-accepting state until we see a grant, and we finish reading the word. And as usual, once we finish reading a word in an accepting state, then the word is accepting. The other example, we start by just not seeing any request. Then we have a request. Then we see a grant. So we are back to the accepting state. But now we see another request, which is not followed by a grant, and therefore this word will not be accepted. So notice that it does have a flavor of regular language, but the regular language consists of several words that relate to each other. And the automaton just can check the relationship between this word while remembering that one comes from one component and another one comes from another component. So again, we have a theorem saying that multi-NFH model checking is reducible to NFH model checking and vice versa. So we didn't add an expressive power, but we can exploit the compositionality. Again, we may construct a direct algorithm with the same complexity as for hyper-LTL and non-deterministic finite hyper-LTL, and for this the specific fragment or of for all star and exist star, we can extract a counterexample. So the setting is very similar, but since we have finite words, we can use automata learning such as L star. So this is what we do. We use L star in order to construct the over-approximation and under-approximation needed by the compositional rule. So we apply the learning for each component separately. In the learning, L star try to learn a deterministic finite automaton for an unknown regular language U. It uses two kinds of queries: membership, in which it asks whether a certain word is in the unknown language, and another one in which we are given an automaton, a deterministic automaton, and we ask whether this automaton recognizes the unknown language. And since this kind of multi-NFH are kind of regular, we can apply L star. In fact, L star, what it does, it has a learner and a teacher. The learner tries to construct an observation table from which it can extract an automaton. And once the table is steady, then we can extract an automaton, which is a candidate automaton sent as an equivalence query to check whether it recognizes the unknown language. So the membership is easy. We just need to, given a word, we need to check whether this word is in the I components in MI. And in the equivalence, we have an abstraction, and we need to check whether the abstraction described by A is, just a moment, is an abstraction of the model M. So I repeat, the equivalence has somewhat different role than in regular L star. It asks whether the abstraction that we computed is an abstraction for the actual model. And now if this specific model, since we have multi-models, if this specific component is quantified by universal, then we require that the abstraction is an over-approximation, and if it is quantified by existential, then we require that the abstraction is an under-approximation. So again, I will not go over the details of the algorithm. The main interesting part here, that again, the learning is applied to each component separately, and therefore we gain not only by using abstraction, but also by computing the abstraction and refining the abstraction for small components, and also by the fact that since each of the component is actually universally quantified or existentially quantified, we can use the over or the under approximating abstraction, where we couldn't do if there was a huge model which is quantified both by existential and universal. I will skip this part and go to the conclusion. So what we did here, we described a multi-property, the framework of multi-properties and multi-models that allow us to suggest compositional proof rules for model checking that exploit abstraction, over-approximation, and under-approximation abstraction for each model separately. We use two types of techniques in order to achieve the over and under approximation. One is abstraction refinement, and the other one is automata learning. And we have the fragment of for all star exist star, in which the algorithms are improved. I didn't go into details here. Okay. Questions?
Thank you, Orna, for a great talk. As before, everyone feel free to put questions in the Q&A box or just raise your hand. And while people are thinking, I had a question about your model checking algorithm. I really like this idea of how if the formula is universal or existential in one model in particular, then you can still use abstraction for that. One question I had there was in the refinement. It seems like all the abstractions, you construct them separately. Whether an abstraction works for a particular formula depends on the abstractions you use for the other models. So when you get a counterexample, like how do you decide whether you should change the abstraction for one particular model or maybe leave it the same and change one of the other abstractions, etc.?
So there were two types of abstraction. One was just behaviors that should be in the abstraction, but they are not there. Mm-hmm. Because for checking the properties, they were missing, and then we know that we need to either add them to the abstraction or to remove them from the abstraction. And for the property, we actually check for the case where for all exists, where we actually get words counterexample for each of the models, then we know that this sequence of words do not satisfy the required properties, and we want to eliminate them. So we know that these are bad behaviors.
Can it not happen then that you have, like, if you have a property which says something like, for all behaviors of the one model, there has to exist some behavior in the other model. It could be that you get a counterexample which says this behavior is not in the second model, but actually you don't need it because the only reason you needed that in the first place was because you over-approximated something in the first model. Does that make sense?
So what we do for exist, we do not use counterexamples because we cannot get a counterexample for exist. So we take just the full model, and then if we have a counterexample, then we need to check whether this counterexample is spurious or not. If it's spurious, then it should be removed from the over-approximation, because in the existential part, we have an exact model. So we couldn't apply actually any abstraction unless we use the other approach where we just found that unrelated to the property, we have a behavior that shouldn't be there. But this is just unrelated to the property, so it's less precise. So we are restricted in handling existential quantification. This is true.
Thanks. Any other questions? Well, I'll ask another one then. So in the last part of what you talked about, where you're using Engluen's algorithm or L star, or the variant of that, I'm curious if you've thought about if there might be some extent, like statistical model checking version of your algorithm where you don't have complete models, say, for some of the systems, and then trying to use a pack version of Engluen's algorithm.
Yeah, it's very interesting extension, but we didn't apply it. Yeah, it's a good way to extend it.
All right. Well, thanks again for a great talk, Orna. Now we have a break until 9, so 13 minutes from now, we'll take a break, and then we will have Bernd's talk right after that. So we'll keep the call running, and we'll start up again in 12, 13 minutes.